Everyone, welcome to the presentation of our work on the privacy risks of deploying recurrent neural networks in machine learning models. My name is Parham Gohari, and I'm a PhD student at the University of Texas at Austin. This is a joint work with Yunhao Yang and our supervisor, Professor Ufuk Topju. I'd like to start the presentation with our approach to privacy. The title of our presentation has privacy risks and machine learning together, but these two domains are very hard to be examined together due to a lack of common vocabulary between them. Privacy is a social concept full of ambiguous and subjective norms and values, whereas AI and machine learning are products of algorithms, and we can actually describe them with computer code. So how do we reconcile these two domains? What we do is that we narrow the scope of our study. In particular, in this research, we focus on vulnerability to a special privacy threat called membership inference attacks. On the left side, you see the common steps in training and deploying machine learning models. During training, we use a training dataset alongside our favorite machine learning algorithms such as stochastic gradient descent, ADAM, RMS prop, and etc. And then during deployment, we would like to use the trained model to make predictions on new data. Now, on the right-hand side, you see an attacker that is trying to get something other than those predictions. Instead, it wants to find out if a data record X was a part of the victim model's training data or not. And in this research, we want to study vulnerability to this specific type of privacy threat. Membership inference attacks are not something that we just discovered for the first time. In fact, they are extensively studied, and we use state-of-the-art MIAs from previous studies, and I will refer to membership inference attacks as MIAs. What we're interested to find out in this study is to examine whether or not a neural network's architecture affects its vulnerability to MIAs. In particular, we're interested in feed-forward and recurrent neural networks. Recurrent neural networks may have backward connections in their architecture, but feed-forward neural networks path from their input to output only goes in the forward direction. Studying the effect of architecture is challenging because there are just too many factors that affect vulnerability to MIAs, so we try to control them. In particular, in all of the experiments, we control the contents of the training datasets because it's just not fair to train on different data and expect to have kind of similar vulnerability to MIAs. We also try to find RNNs and feed-forward neural networks that perform similar to each other, roughly speaking. Generalization power is important in vulnerability to MIAs, and we try to control that factor too. And then lastly, we also control the number of trainable parameters because that has also been shown to have an effect on vulnerability to MIA. We were able to control these factors in three setups. Image classification, where the agent needs to label images regarding their content. Machine translation, which is straightforward, we use German to English. And deep reinforcement learning, where an agent must reach a predetermined location in a grid world example. We're now ready to take a look at the first set of experiment results. In the first experiment, we take an initial look at model performances and MIA attack accuracies. In the top row, we see the training and validation accuracy of the models across 3 machine learning tasks, and in the bottom, we see the attack accuracy against the number of training epoch. What we see here, which motivated us in the first place to pursue this research, was that the MIA accuracies for RNNs are considerably above those of feed-forward neural networks. What's striking is that generalization power that plays a key role in vulnerability to MIAs in the following way. Models with better generalization powers are often less vulnerable to MIAs. We're seeing a reverse relationship here. In some cases, we see that the generalization power of RNNs is better than feed-forward neural networks, but they score lower in terms of MIA accuracy. So the key takeaways here is that we see a trend in higher attack accuracies in RNNs. And also we see that the generalization power is not the only factor in vulnerability to them, because we are seeing the opposite relation in RNNs as well. So we try to see if not generalization power, then what? In the second set of experiments, we take a look at the model's prediction entropies and their associated MIA accuracy. What is measured in entropy is uncertainty in the following way. If I have a prediction of 0.99%, 99% confidence in one category and 1% confidence in another one, my uncertainty is very low, and entropy will give me a number that's low too. But if I'm 50-50 on a prediction, then I will have the highest level of entropy. Now, this experiment sheds a big light on what is really happening in recurrent neural networks. We can see that RNNs maintain a higher gap in their prediction entropies between training and validation early in the onset when the training starts. But once the gap becomes identical between RNNs and feed-forward neural networks further in the training, the attack accuracies become close to. But it seems like during training, the RNNs reveal membership through making predictions with noticeably less uncertainty, such that MIAs can pick those differences in the prediction. So the key takeaway here is that the gap between training and verification entropy seems to be related to MIA attack accuracies closely, and that the gap in RNNs is generally higher compared with their feed-forward counterparts. In the next experiment, we asked this question. Okay, so we know that the entropy gap is larger in RNNs, but do MIAs actually pick that up? Is that a part of the MIA's decision-making scheme? Also, it is likely that non-member data predictions are less accurate in verification. So we take a look at an MIA's decisions and map it on a 2D plane between prediction loss and prediction uncertainty. What we think initially is that accurate predictions with high certainty should be labeled as member data, and those with less certainty should be labeled as non-member. But what about those with less accuracy? It could be the case that they were out of distribution, so they were actually non-member data, or that the algorithm saw them during training but just failed to learn their pattern. So let's find out. And what we did was to just plot and give a bunch of data, form a data set of member and non-member data, and then look at the decisions that the MIA makes across the three tasks that we have. So the red markers show non-member data, and the blue markers show member data. And then the circle markers are successful MIA inference, and the X's are the failed MIA. What we observe here is that the MIAs indeed label accurate predictions with low uncertainty as member data. Although it does make mistakes in those predictions, especially in image classification, but the overall trend is that accurate predictions with low uncertainty are marked as member by the MIA attack. And this is very similar to what we expected initially about that too. So now we move on to another experiment that we designed to study the effects of model memorization. What we did was that we partitioned the training data sets into an ordered sequence and introduced the partitions incrementally during training. Then we measured the MIA accuracy with respect to each partition. Roughly speaking, RNNs such as LSTMs, they have memory cells, and that just piqued our curiosity to see how that memorization will affect vulnerability to MIAs. What we observed for the three machine learning tasks that we consider is that both architectures to some extent memorize their training data. And we say they memorize their training data because the MIAs are able to use the patterns in their predictions to infer membership. In feed-forward neural networks, however, the MIAs cannot go farther than a couple epochs. Notice that 50% here is random guessing, and that's the worst thing that they can do. And in feed-forward neural networks, the MIAs go to 50% in a couple epochs. However, in RNNs, the MIA is maintaining 60% accuracy for even older epochs of data. In the next experiment, we move on to defense mechanisms against membership inference attacks. Perhaps one of the easiest defense measures is to reduce overfitting, which is something regulation methods do. They're particularly useful because not only they protect against MIAs, they improve the model's general performance and generalization power too. We now examine how regularization affects the two architectures. In another blow to recurrent neural networks, we see that regularization doesn't do much for recurrent neural networks. And when it does, for example, in deep reinforcement learning, the slope of the improvement isn't as high as in feed-forward neural networks. Next, we look at the defense mechanism that provides the theoretical defense guarantees against membership inference attack, and its name is differential privacy. Roughly, what differential privacy does is to make it hard to observe the output of an algorithm and relate those outputs to the individual entries of the algorithm's input datasets. For example, if we have two candidate datasets, D and D dash, the worst outcome with respect to attack accuracy in MIAs is if the MIA can infer with perfect accuracy if the input that was used for this function was D or D dash. And that's the origin of this plot that I'm showing you in terms of type 1 error and type 2 error, false positives and false negatives. What happens with differential privacy, I'm not going to get into the details of it, but roughly speaking, is that almost always there's a chance that the MIA has either a large type 1 error or type 2 error, and we can guarantee that theoretically. This is not just empirically. So there are several ways that differential privacy can be enforced in the training of neural networks, and enforcing it is not a contribution in this work. But we just wanted to see how enforcing differential privacy, the effects of it differs across recurrent neural networks and feed-forward neural networks. What enforcement mechanisms typically do is to add noise to some important variable during the training. For example, in DPSGD algorithm, the noise is added to the gradients, and sometimes it's added to the parameters. And we examine these too. In the next example, we examine how the noise affects RNNs and feed-forward neural networks. Here we use the same noise variance, which leads to the same level of differential privacy. And then we measure the utility loss as a cost of privacy. And again, we see that the recurrent neural networks take a bigger blow to their utility loss than feed-forward neural networks. So that was all I wanted to show you today. And here's a summary of what I showed you. We saw that the prediction entropy gaps between training and validation is generally higher in RNNs, which we suspect is the main cause of higher vulnerability to MIAs. We saw that the MIAs have a hard time for getting sequential batches of data. We saw that regularization isn't as effective in recurrent neural networks. And finally, we saw that enforcing differential privacy has a higher price tag in RNNs than feed-forward neural networks in terms of loss of accuracy. Thank you for listening. I hope you enjoyed my presentation, and let me know if you have any questions.